Welcome back, ladies and gentlemen, to the next video in the Introduction to Mathematics course. Today we're going to talk about relations, graphs, and orders. So, relations are a special class of sets, and so special that they do deserve their own video. And they describe in a mathematical way what you would ordinarily understand under the term relations. So first we introduce the mathematical notions of relations, and then we're going to have a quick look at graphs. And graphs are a good way of representing relations, and that's why we introduce them here briefly. And in the last section we'll study an important special kind of relation, the so-called order relations. So in this video there will be mainly some new concepts introduced and a lot of examples and only very few proofs. Before we begin, if you want to relate better to me and my content, then this is the golden opportunity for you to like this video and subscribe to my channel to support me creating more content in the future. So let's start with relations. And for this chapter, it is important to be familiar with Cartesian products. So I introduced those in chapter 3 of this course, the Cartesian products of sets of 2 or 3 or 4 or multiple sets. And we all know what relations are, and there are many different kinds of them, and we will now explore a few examples to ease into the mathematical definition of relations. Our first example: Alice is married to Bob, and here being married to defines a relation, in this case between Alice and Bob, but of course there can be other people who can be married, so it makes sense to generalize this to a predicate. X is married to Y, where X and Y are taken from some set H, which is in this case the set of all human beings. And we can also express other relations, such as Bob is taller than Alice, which has the general form X is taller than Y, and again X and Y would be elements of the set of human beings. And we immediately understand that both of these are relations in the usual sense of the word, but also that the quality of these two relations is rather different. And this is something that will become clearer later on once we define some properties of relations. Now, how to express such relations mathematically? We can formalize this a little bit more by saying that each married couple XY is actually given by a pair XY in the Cartesian product of the set H with itself, H times H. So the set of all married couples, the set of all these pairs, is actually a subset of this Cartesian product, H times H. So we denote this by the Greek letter mu and say the marriage relation is given by this subset of pairs XY, where X is married to Y in the Cartesian product of the set of all humans with itself. And this idea can be turned on its head and used to define the possible relations between two elements of H. Namely, we define them to be subsets of the Cartesian product H by H. So in this way, any relation is solely defined by the members it contains. So we take the set of all the objects that are related, and then we say, well, this set just is our relation. And of course, this contains no information about the quality of the relation, so whether it's married to, at war with, or taller than. So this is something that has to depend on the context in which we use this subset as a relation. And also we can consider relations between more than two objects, and not all related objects have to be taken from the same set. For example, let's say we have this relation here, Alice and Bob got married in Paris. Then again we have Alice and Bob being married, but we also have a city here. So this corresponds to the relation, to the subset of the triples x, y, c, taken from the set h times c, where h is again the set of humans and c is the set of all cities. And then such a triple being contained in the subset means x and y got married in C. So two people, x and y, got married in the city C. And one element of the set would be Alice and Bob and Paris, this triple. So we make the following definition based on our previous thoughts. Let x1 to xn be sets, so a finite number of sets, and then a relation between these sets x1 and xn, or rather between the elements of these sets, is defined to be a subset rho of the Cartesian product of the sets x1 times x2 and so on times xn. And we say that elements x1 from the set big X1 and so on, xn from the set big Xn, are related by rho if the tuple x1 to xn is contained in rho, is contained in this subset of the Cartesian product. And an important remark on the terminology here. Some authors call what we define here a correspondence and call it a relation only if all of the sets x1 to xn are actually identical. However, this distinction is not so important, since we can always assume that this is the case by simply replacing each of the individual sets xi by the union of all of them. So instead of our individual sets here, we just take the union of all of them, call them x, and then our relation rho here just embeds into this Cartesian product of the set x by itself n times. So again, this is not the most important distinction between correspondences and relations. Now in the following, we will almost exclusively study binary relations, so where we have two sets n equal to 2, and we will usually have it that the two sets are identical. So in this situation, we will use the shorthand notation as follows. If two elements xy are related by rho, we simply write x rho y. And when we look at concrete relations later on, such as the order relations, this notation will actually make a lot of sense. And here's a little exercise for you. For any set x, the diagonal relation of the Cartesian product x is the relation delta that contains all the pairs xx for arbitrary elements of the set x. So all the pairs where both entries are identical. And I'll pause the video for a minute and think about what this relation expresses. So this relation delta expresses the equality of elements in x. We have x delta y if and only if x is equal to y. So that's maybe a bit of an overblown way of writing equality, but it's actually a very helpful idea to be able to express equality through this relation delta. We will use this later on and also in the upcoming video on equivalence relations. Let's look at another example. So we already learned about the graph of a map. So if we have a map f from a set x to a set y, then this graph is in fact a relation on the set x times y. The graph of f was defined as the set of pairs x and f of x. So x taken from the set big X, and f of x takes its values in y. So here's an element of the set big Y. And this relation obviously expresses that a pair xy is contained in the graph f relation if y is the value of x under the map f. Now we could compose maps between sets with one another. See chapter 3 of this course for that. And in a similar way, we can define composition of relations. So if x, y, and z are sets, and rho is a relation between x and y, and sigma is a relation between y and z, then we can define the composition of these two relations of rho and sigma as follows. Sigma composed with rho is the set of all pairs x, z, where x is taken from the set big X and z is taken from the set big Z, such that there exists some element y in the set big Y, such that xy are related by rho and yz are related by sigma. And in the special case that rho is a binary relation on the set X, so rho is a subset of a Cartesian product x times x, and we compose it with itself, then we can use the usual shorthand notation rho squared for rho being composed with itself, or rho to the power of 3 for rho being composed with itself twice, and so on. And obviously the obvious notations for higher compositions of rho with itself. Now, as a little exercise that I'm not going to explain any further here, please convince yourself that the composition of the relation graph G with the relation graph F is the same as the relation graph of the composition of maps G composed with F. And as I said, I'm not going to give the solution for that because it's basically just careful thinking about the definitions of the two compositions that are involved here. Let's see an example where we can employ this composition of relations. So let S be the set of students at some university, T the set of topics that is being taught at this university, and B the set of books in the university library. Then we can define all kind of relation between these sets. So for example, this one, the relation rho between the students and the topics is defined as follows: S rho T. S, the student S, is related to the topic T if student S is interested in topic T. And another relation sigma defined on the set of topics and books is the relation defined by T being related to B via sigma if the book B covers the topic T. And now we can form the composition of these two relations. Sigma composed with rho is the following relation. It consists of all pairs S and B, such that there exists some T in the set of topics, such that the pair ST is contained in rho and the pair TB is contained in sigma. Or a bit more explicitly, there is a topic T that is interesting for S and that is covered in book B. So intuitively we could state that the composed relation sigma composed with rho holds for a student S and a book B if the topic of book B is interesting for student S. And you can imagine that such constructions can be interesting for example database applications. Now we want to learn more about the properties of relations to distinguish better between different kinds of relations. So X is a set, and we have a binary relation rho on X. Then we say that the relation rho is reflexive if X rho X for all elements X in our set big X. So every element is related to itself. Then we say rho is reflexive. We say that the relation is irreflexive if no element X is related to itself. So note that this is much stronger than just saying it's not reflexive. Not reflexive would just require that there's one element that is not related to itself, but irreflexive actually requires that no element is related to itself by rho. We call the relation symmetric if for all elements x, y in the set X, X being related to Y automatically implies that Y is also related to X. So this means saying X rho Y is equivalent to saying Y rho X. And we say the relation is antisymmetric if whenever X rho Y and Y rho X both hold, then it must already imply that X and Y are identical. So this and this together cannot happen for two distinct elements. It can only happen if X and Y were identical to begin with. We say a relation is transitive if for any three elements X, Y, Z in our set big X, if we have X being related to Y and Y being related to Z, then we also must have X being related to Z. And the last property in this list is that we call rho alternative if for all elements X, Y in our set, at least one of X rho Y or Y rho X holds. So any two elements are related in one way or the other, possibly both, but that's not required. It's just required that either X is related to Y or Y is related to X. That's what alternative means. So, as a little practice, let us check these properties for our first examples. The marriage relation, so recall it was this one, mu, the pairs xy in the Cartesian product of the human set where the relation means X is married to Y. Now, this relation is not reflexive since people are not married to themselves. In fact, it is even irreflexive because nobody is married to themselves. So X mu X does not appear in this relation. The relation is, however, symmetric, since if X is married to Y, it also means that Y is married to X. The relation is not transitive. That would be quite a complicated society. So even if we think it possible that polygamy exists, it is not clear that if X were to be married to Y and Y is married to Z, that this would imply that X is married to Z. Now, if we would enforce a very, very strict monogamy, where every person X can only be married to precisely one person Y, then this actually would turn out to be transitive by the symmetry of the relation, but that would be a trivial statement then. It is not alternative, because alternative would require that any two arbitrary people picked from the set H would have to be married to each other, and that is clearly not the case. Now the second relation we had in our first example was the taller relation. So we call this relation tau. It's the pairs xy, the set of pairs xy taken from the human being set, where being contained in the set tau means that x is taller than y. Now, this is not reflexive since nobody is taller than him or herself. In fact, as with the marriage relation, tau is irreflexive. It is not symmetric because if x is taller than y, then necessarily y is not taller than x. It is transitive, however, because if x is taller than y and y is taller than z, then x must also be taller than z. It's not alternative since there could be two people which have exactly the same height, so neither one would be taller than the other. Now we could modify this relation a little bit, and instead of asking for taller, we say x is at least as tall as. So taller or same height. And if we would weaken the relation like that, then it actually would turn out to be alternative, because between any two people, either one of them is taller than the others or they have the same height. Now, this taller relation is actually an example of an order relation, which we will study in more detail later. But before we study order relations, I want to introduce you to graphs. Graphs are a great tool for visualizing binary relations, and they're rather easy to understand intuitively, but if you want to derive some of their more interesting properties, you have to treat them as mathematical objects. So in this section, I want to give you an idea of how mathematical graph theory is formulated to enable you to read and understand texts on graph theory by yourself. As I said, a great way to visualize binary relations, rho, subset of x times x, are graphs. And here we represent the relatable objects, so the elements of x, by vertices, and we connect them with an edge if they are related by rho. More precisely, we define a graph G to be consisting of a pair of sets V and E, where V is a set of vertices and E is a relation on V, and we call E the set of edges. If the relation E is symmetric, then we say G is an undirected graph, and otherwise we say that G is a directed graph. Here we think of the pair V1, V2 in the set of edges as representing an edge leading from vertex V1 to V2. So this situation here, if this is vertex V1 and this is vertex V2, and we have the pair V1, V2 contained in the set of edges, then we have this directed edge from V1 to V2. Now if we have a symmetric graph, then having the edge from V1 to V2 automatically implies having the edge from V2 to V1 as well, so the reverse edge. And in this case, we do not have to assign direction to the edges, because in a symmetric graph, this is the case for all edges. So this would be seen here. For any edge in this direction, we have the reverse edge. And so instead of having both edges here explicitly, we could just have one undirected edge between the two vertices. So in undirected graphs, we count the two edges VW and WV as one and the same edge. So we don't count them as two edges, even though there are two elements that appear in the set of edges, but we just count them as one. And this is important to remember. It is often quite cumbersome to keep track of the distinction between directed and undirected graphs. And for undirected graphs, it seems quite unnatural to count every edge twice, just because they appear twice in the definition here. And that's why we agree to count every pair of mutual reverse edges just once in undirected graphs. So here we have an example of a directed graph with 4 vertices, A, B, C, D, and our set of edges, which are indicated here by these arrows. And there are 3 different ways of visualizing the same graph. So these are not distinct graphs, but they're actually all the same. And this is a very simple example that demonstrates that there are different ways to visualize an abstractly defined graph, so defined by V and E, and that not all of these visualizations are aesthetically pleasing in the same way. The next is an example of an undirected graph with, again, vertices A, B, C, D, and E, so one more vertex actually. And here in the set of edges, we see that for every edge AB, we have the reverse edge BA, BC, we have CB, and so on. So we don't need to draw them as arrows because they always go in both directions. We use the following notations when we count objects in graphs. So for a directed graph, G with vertex set V and edge set E, we use this notation for the cardinality of V. So assuming that we have a finite set, then this is the number of vertices in the graph. And straightforward for the edges, we use this notation for the cardinality of the edge set. For an undirected graph, it's very similar. We count the vertices in the set V, but if we count the edges, then we take 1/2 the cardinality of the set of edges. So this is exactly what I described before, because we automatically have the reverse edge for any given edge in the undirected graph, so there's no point in counting them twice. Now, if G with vertices E and edges E is a graph, and we suppose first that G is undirected, then we define the degree of a vertex in this graph, written deg V, to be the cardinality of the set of edges such that the edge contains V as its initial vertex. So in other words, the degree of V is the number of edges connected to V, to the vertex V. And now suppose G is a directed graph, then it's a bit more complicated. So first we define these 2 sets here. I call this V out. It's a set of edges that have V as their initial vertex. And I call this V in. It's the set of edges that have V as their second vertex. So this is a set of edges leaving from vertex V, and this is a set of edges arriving at vertex V, and we can count those. And then we say the out degree of the vertex V is the cardinality of this set V out. So the number of edges leaving from vertex V. And the in degree of vertex V is the cardinality of the set V in. So the number of edges arriving at the vertex V. And now a little exercise for you. Pause the video for a moment and determine in and out degrees for the vertices in this directed graph. and also determine the degrees of the vertices in this undirected graph. The solution here, I just quickly go through it. So for the vertex A, you see we have 3 outgoing edges, so we have out degree 3, but there's no incoming edge, so the in degree is 0. Then for B, we have 1 outgoing and 2 ingoing edges, so out degree 1, in degree 2. For C, we have no outgoing edges, so the out degree is 0, but we have the 3 incoming edges here, so the in degree is 3. And for D, we have 2 outgoing edges, 1 to C, 1 to B, and the 1 incoming edge from A, so out degree is 2 and in degree is 1. And here in the undirected graph, we just have to count the edges at each vertex, so there's degree 1 for A, degree 3 for B, because 1, 2, 3 edges here. For C, we have degree 2. For D, again, we have degree 3. And for E, we have degree 1. Now, if we're given a graph, we can look at subgraphs. And by a subgraph, we mean a graph G' with vertex set V' contained in the vertex set of our original graph. And the edge set E' of the subgraph must consist of all the edges between vertices in V'. So formally, E' is the set of pairs V1, V2, such that the vertices are contained in V', and there's an edge V1, V2 in the set of edges from our original graph. And another way of expressing this is the intersection of E with the Cartesian product of V' with itself. Now, this definition does not allow us to arbitrarily drop edges from the original graph G, but only those edges where one vertex is not contained in the new vertex subset V'. And sometimes there's a more general definition, a somewhat looser definition used for the subgraph, which only requires that E' is contained in the intersection of E with V' times V'. So that means we could, in this more general definition, we could drop some of the edges in this set here, but we could not include any edges, of course, where a vertex is not contained in V'. Now here's an example, or actually 2 examples of subgraphs from our previous undirected graph. Here we take as the vertex set V', B, C, and D. And then the set of edges must be all the edges connecting any of these vertices in the original graph. So the red ones here. And similarly, we have BDE as a subgraph here. And this set of edges must then be all the edges connecting B, D, or E in the original graph. If we were to use this more general definition, then for example, we could remove this edge from the red subgraph and have only this part here as a subgraph. And this would not be a subgraph by our more strict definition up here. So in a relation row, it could be that 2 elements, x and y, are not related to one another, but that there's a sequence of related elements leading from x to y. So what do I mean by that? There could be some more elements x1, x2, xn, and so on, such that x row x1, so we have x being related to x1 row x2, so x1 being related to another element x2, and so on. And then we arrive at some element xn that is related to y by the relation row. And in the graph visualization, this sequence gives rise to a walk in the graph. Now, to define this precisely, if we're given a graph G and two vertices VW in this graph, then a walk of length k from vertex V to vertex W is a sequence of vertices V0, V1, up to Vk, such that the sequence begins with our vertex V and it ends with our vertex W. And any two vertices that follow after one another in the sequence are connected by an edge. So the pair Vi minus 1, Vi is contained in the set of edges for all indices I from 1 to k. And then we call this a walk. Now if the start and end vertex are identical, so V equal to W, then we call this walk a circuit. We say the walk is simple if no edge appears twice in it. So all the edges here are all unique in this walk. And we say a path is a walk in which no vertex appears twice. And of course, if no vertex appears twice, that means that no edge can appear twice, because if it did, then the vertices in this edge would appear twice. So any path is in particular also a simple walk. And a circuit in which no vertex other than the start and end vertex appears twice is called a cycle. And then a loop is simply an edge from one vertex to itself. Or you could also call this a circuit of length 1. And unfortunately, the terminology for all this, for walks, circuits, loops, and all that in graphs, is not standardized throughout the scientific literature. So you will quite likely find these terms here used with different meanings in some books or lectures. So be aware of that, and whenever you read of a path or a walk or a loop or a cycle, make sure you know what the definition is in whatever source you're reading it. Here we have an example where I want to illustrate walks, paths, cycles. And this graph actually represents something, and you might want to guess what that is. And if you have any good guess, please write it in the comments to this video. Okay, first we have a non-simple walk of length 10, starting at vertex 1, ending at vertex 9. So first we go from 1 to 6, then to 7, 8, back to 6, down to 2, 4, 5, 6, then to 1, so we use this edge twice already, and then finally to the end vertex 9. A circuit is where we arrive at the initial vertex again, so from 1 to 7, 7 to 6, 6 to 2, 4, 5, 6, and back to 1. Here we have a path of length 5, so no vertex is used twice in this path. From 1 to 9, 9 to 8, 8 to 6, 6 to 2, and 2 to 3. And here we have a cycle of length 5, beginning and ending at 1, so no vertex other than the initial vertex is used twice. We go to 7, to 6, to 8, 9, and back to 1. And if it is necessary for reasoning about the properties of a graph, we can always replace walks by paths and similarly circuits by cycles. So we can sometimes simplify arguments by assuming that no vertex or no edge in a walk or in a path is used twice. This is the statement of the following lemma. If a graph contains a walk of length k from vertex v to vertex w, then this graph also contains a path of length at most k from v to w. And this may seem intuitively clear if you think about it, but it's a good opportunity for us to finally prove something in this lecture. So suppose there is a walk v0, v1, vk minus 1, vk, starting at v, ending at w. Now, if this walk is not already a path, then some vertex vi appears at least twice in the path. So it appears at least twice in this list here. So we have two indices e, I, and j, where I is strictly less than j, such that vertex I is identical to vertex j. So these being the two distinct positions where this vertex appears. And now we can replace the original walk by the new walk, v0 up to vi, and then we continue at vj plus 1 and go to the end vertex vk. So if the vertex vi appears twice, then we just cut out the whole bit of our walk up until the second appearance of vi, and we get a shorter walk by doing this, of course. So the length is smaller than k in this case. And we repeat this until there are no more duplicate vertices in the walk, and then we have a path from v to w necessarily, because that's just what the definition of a path is, that every vertex appears at most once. Now, for an undirected graph G, we say that it is connected if any two vertices can be joined by a path. So if we are given arbitrary vertices v and w, there's some path starting at v and ending at w. And because it's an undirected graph, then of course we have the reverse path going from w to v. What this means is that given any undirected graph G, we can partition the set of vertices into disjoint subsets of vertices. V, the vertex set, is a union of disjoint subsets, v1, v2, and so on, where either the subset vi contains exactly one vertex, or if it has more than one vertices in it, then two vertices v and w are contained in vi if and only if they are connected by a path in G. So in this situation here, if we let ei denote the subset of E containing the edges between the vertices in vi, then we call the subgraphs obtained by taking the sets vi and their corresponding edge sets ei the connected components of the graph G. So it follows from the choice of this decomposition here that all these vi's are connected, and so it's justified to call them connected components. And also that between these disjoint subsets there are no edges going back and forth, because then otherwise the vertices would have to be contained in the same set. Now, here we have a graph with four connected components, G1, G2, G3, and G4. So in fact, G3 contains only one vertex and not a single edge. And yeah, you see, obviously the connected components are connected, but the graph overall is not connected. Now I should not forget to mention two of the most important properties in the theory of graphs, namely these two important types of paths. A circuit in a graph is called an Euler circuit if every edge of the graph, of the whole graph, appears precisely once in it. And a cycle in a graph is called a Hamilton cycle if every vertex of the graph, other than the start vertex, appears precisely once in it, and the start vertex appears only once again as the end vertex. So recall, for a cycle it was required that all the vertices in it, other than the start vertex, appear at most once. And here we have a cycle that contains every vertex of the whole graph. And it's a very famous, difficult problem in theoretical computer science to determine whether a given finite graph contains a Hamilton cycle. So this is a so-called NP-complete problem, which basically means it's a very, very hard computational problem, and there are no known ways of solving it in an efficient manner. And for Euler circuits, on the other hand, there exist some reasonably efficient algorithms to determine whether they exist in a graph or not. But by reasonably efficient, I mean that they have polynomial runtime, if you know what that means. And the next theorem will give a criterion for the non-existence of Euler circuits. Actually, a very simple one. So let G be a connected, undirected graph without loops, so without edges from a vertex to itself, and on a finite vertex set V. Then if G has an Euler circuit, all its vertices must have even degrees. And the proof is as follows. Imagine we follow the Euler circuit from vertex to vertex and delete each edge once it has been traversed. So doing this does not cause a problem, because in an Euler circuit each edge appears only once, or precisely once, but in particular this means only once. So if we delete an edge, we don't need it further on to traverse the circuit. So we can do this without problem. Now in this way, for each vertex Vi in the Euler circuit, we erase one edge, Vi minus 1 Vi, when we arrive at the vertex Vi, and we erase another edge, Vi plus 1, when we depart from Vi. And this is because loops do not exist in the graph, so we can make this statement. And this reduces the degree of vertex Vi by 2 every time we walk past vertex Vi, we erase the incoming and the outgoing edge. So it reduces the degree by 2. And for the start vertex V0, we erase the first edge and the last edge of the circuit. So eventually all edges have been deleted when we're done walking through the path or the circuit. And once we're done, all vertices have degree 0. So because we arrive at this point by in each step reducing the vertex of a degree by 2, all the vertices must have had even degree to begin with. And that concludes the proof. And now I have a little exercise for you, so pause the video for a few minutes, maybe a few more minutes in this case. And first find an Euler circuit in this graph here. Now this is the so-called complete regular graph in 5 vertices. It looks a bit like the House of Santa Claus graph, but it's not quite the same because it has these 2 additional edges here. And the second task for you is to look up Euler's Königsberg bridge problem, understand it, and use theorem 21, which we just had on the slide before, to solve it. Now for this problem, it's important to understand that the theorem holds in exactly the same way for so-called multigraphs. So multigraphs are just graphs where we allow more than one edge between two vertices. So please do these exercises now. Okay, I hope you invested some time in this. So here in our not quite House of Santa Claus, we have the following Euler circuit. We start at this vertex here, so we could have started at any other vertex. There are many different possibilities, so this is just one. And this is not quite the House of Santa Claus. Beautiful. So we arrive at the end again after having used each edge in the graph precisely once. Now, the second part, the Königsberg Bridge problem, was posed by Euler, and that's actually where the name Euler circuit comes from. And back in Euler's day, the city of Königsberg had 7 bridges. So there's this river called Pregel running through the city, and the different parts A, B, C, D of the city were connected by these 7 bridges that are indicated here. And Euler basically asked the question, can I walk through the city using each bridge precisely once and arriving at the same point where I left? So in other words, he asked, is there an Euler circuit in the city of Königsberg if we take the parts of the city as the vertices and the bridges that connect them as the edges? Now this is the graph version of this. So you see there are 2 edges between vertices here, so that's why it's called a multigraph. And by our theorem 21, we find that in fact there can be no Euler circuit because the vertices here do not all have even degrees. Actually, they all have odd degrees. So theorem 21 tells us that there's no Euler circuit. Next, we introduce a particular important class of graphs, the so-called trees. Now, a tree is a connected, undirected graph without cycles. And if we drop the connectivity, then we get a forest. So a forest is a graph whose connected components are trees. And here, this little image just is an example of a tree. Then we have the following proposition. If we have 2 distinct vertices, V and W, in a tree, so the trees are called T, with vertex at V and edge at E. So if we have these 2 distinct vertices, then there's a unique path connecting V and W. And this may seem obvious, and yeah, indeed, the proof is very short. But it's still important to remark this. So since the tree T is connected, there's at least one path going from V to W. So we could say there's at least one walk, but if we have a walk, then we always have a path, as we've seen before in this lecture. Now assume there are 2 distinct paths going from V to W, then we could traverse the first path from V to W and then go the second path backwards from W to V. We can do this because trees are undirected. And in this way we would obtain a circuit. But a circuit contains a cycle, since V and W are distinct, and so we're contradicting the definition of a tree, because trees are required to not contain cycles. And thereby we have shown that there's a unique path from V to W. And now we have this proposition as the final result of this lecture. In a tree T with vertex set V and edge set E, assuming that they are finite, the cardinality of the vertex set is the number of edges plus 1. Again, this may seem obvious from looking at a few examples, but This is another good opportunity to practice casting our intuition into a precise proof. And we do prove this by induction on the number of edges. So I call this M, the number of edges, which is greater or equal to 0. The initial case in the induction is where M is equal to 0, but that means we don't have any edges, and so there can be only one vertex in the tree. Because if we had 2, then we would have 2 unconnected vertices, and that would contradict the definition of a tree. So there can be only one, so we would have one vertex, and that's 0 plus 1. Perfect. The induction hypothesis is simply that this claim here is true for every tree with at most m edges. The induction step needs a bit more space, so we do it on the next slide. We continue the proof with the induction step. So now we take a tree T with m plus 1 edges. So here this quantity E, or number of E, is m plus 1. And then we pick any edge in the set of edges and remove it from our tree. So if this is our original tree, T, then we pick one edge, this one for example, and we remove it, and we get 2 trees after that. And of course these are trees which have fewer edges than the original tree T. So this procedure splits T into 2 subtrees. So I use the colors red and blue as I indicated it here in this example. So T1 and T2, such that the number of vertices of the original tree is the number of vertices of the first tree and the number of vertices of the second new tree that we obtained. And the number of edges in the original tree is 1, namely the one that we removed, plus the number of edges in the one new tree that we obtained, and plus the number of edges in the other new tree that we obtained. Now, both of these trees T1 and T2 have less than m plus 1 edges, so we can apply the induction hypothesis to each of them. So we have the number of vertices, which was this one, by the induction hypothesis being equal to, well, the number of vertices in subtree 1 is by induction hypothesis identical to the number of edges in subtree 1 plus 1, and the number of vertices in subtree 2 is by induction hypothesis identical to the number of edges in subtree 2 plus 1. Now, what do we have here? We have number of edges in E1 plus 1 plus number of edges in E2. And by this equation here, if we combine these together, this is just the number of edges in our original graph. But then we have an additional plus 1. So we have here number of edges in T plus 1 equals number of vertices in the tree. And that is precisely the formula we want for m plus 1 edges. And that concludes the proof. Now we study order relations. So the notion of an order relation is almost self-explanatory. Such a relation allows us to compare elements in a set and arrange them in an ordered fashion, as long as these comparisons make sense. And the quintessential example of such an ordering is, of course, the ordering of numbers. And this could be natural, rational, or real numbers. So we look at this example first, and for simplicity, just stick with the natural numbers. So we know that natural numbers are ordered simply by their size. So this gives us a relation less or equal and I will simply use this symbol as the name of the relation. So maybe this takes a bit getting used to, but now the less or equal symbol is the name of this subset of the Cartesian product of the natural numbers. And I will do this with the other order relations as well. Now we can compare two elements m and n in the natural numbers by their size. And for example, 5 is less or equal to 6. So 5 is related to 6 in this sense. 0 is less or equal to 1. 100 is less or equal to whatever this number is. And 9 is less or equal to 9. Now there's a corresponding strict order relation, which I simply denote by the less symbol, which can be defined as the relation less equals the relation less or equal without the diagonal relation. So recall this diagonal relation from the earlier exercise we had in this video. This is the relation which contains precisely the identical elements n. So if we take those out of our less or equal relation, then we get the strictly less relation here. So pairs such as 9, 9 are included in the less or equal relation. So here 9 less or equal to 9 is true, but they're not included in this stricter relations because 9 less than 9 is not true. Okay, so this is what it means. We take out the elements of delta of the diagonal relation, and 9, 9 is precisely such an element that would be contained in delta and is no longer contained in the strictly less relation. These orders on numbers we take as given here, so of course you all know them. A precise mathematical definition of these less or equal or strictly less orders can be given once we've seen an axiomatic construction of the natural numbers, but this is a topic for another course. We continue this example and look at some of the properties that the order relations on the natural numbers have, and this will lead us to a general definition of orders. So both order relations, the less or equal or the strict one, are transitive, since for natural numbers, if m is less or equal to n and n is less or equal to r, then this of course implies that m is less or equal than r. And the same holds for the strict relation. In addition, the less or equal relation is anti-symmetric, since if we have both that n is less or equal to m and m is less or equal to n, then we must have n being equal to m. Now formally you could say that the strict relation also has this property, but in fact this is an empty condition on the strictly less relation, because n less than m and m less than n never hold. So you could say this implication here is true even for the strict relation, but that is only the case because the assumption of the implication is never satisfied. So it's an empty condition. Now, less or equal is also reflexive, since n is less or equal to n for every element in the natural numbers. And it is alternative. Recall what that means. It means that all elements m and n can be compared. That is, we either have m less or equal to n or we have n less or equal to m. One of the two always holds. Now, this is almost true, but of course not true for the less relations, because we do not have n strictly less than n for any n, so that's why it's not true. But for any distinct pair of numbers, we always have that either n is less to m or m is less than n. But so these are properties for less or equal, but the less relation has the property of being irreflexive, precisely for what I just said before. N strictly less than n does not occur for any natural number n. Now, this example motivates our definition for order relations in an abstract sense. So if X is a set and omega subset of X times X is a relation on X, then we call omega a partial order if omega is reflexive, anti-symmetric, and transitive. We call it an order if it is a partial order and in addition alternative. So it has all these properties, and in addition any two elements of the set X can be compared by this relation omega. And other names used for this are also total order or linear order, because in the literature sometimes the word order is used instead of partial order, or it could be used to mean either partial order or a total order. So that's why there are different names for this concept flying around. But here I will simply speak of an order if it's a partial order and alternative. And the strict order, or also strict partial order, so the distinction is not that relevant here, is omega if it is irreflexive and transitive. So if any of these is the case, then we say that the pair of the set X and the relation omega is a partially ordered set, or an ordered set, or a strictly ordered set, depending on which case we have. And in addition to using Greek letters for our relations, we will often use more expressive symbols to denote orders or partial orders, such as these. So this one you know, the less or equal symbol, then that's a variation of it. This one you know from the subsets, and here this is kind of a variation of the subset symbol. Here we have the strictly less symbol and its curly variation. Now from subsets, recall that it was a bit unfortunate because the notation is not very intuitive. This symbol here usually does not mean a strict subset, so it's often used equivalently with this one, and so we have introduced this symbol here to emphasize that something is a subset but not identical to the superset. Yeah, that's just a bit unfortunate that the convention is that way, that this one has not been established consistently to mean a strict subset, but what can you do? Yeah, and then this one is the strict version of this last symbol here. Yeah, so whenever we use one of these symbols, it's suggestive to mean that we are looking at some kind of order relation. And we will also use some obvious notation that I don't want to have to define in a formal way. So if I write something like x less y less z, then this simply means the same as saying x is less than y and y is less than z. And similar, if I use something like greater or equal, so x greater or equal y, this is just another way of saying y is less or equal to x. So of course you could also introduce this as some kind of a relation, but yeah, I will just define the notation to mean this. And yeah, some other obvious notations that are derived from that I don't want to have to go to great length to define here. You will understand them when you see them. Now, we had this strict order on the natural numbers, corresponding to the less or equal order. And in a similar way, we can associate to any partial order in a strict order. And we do this as follows. Given any partial order omega on a set X, we obtain a strict order, which I call omega hat, by setting omega hat to be the complement of the diagonal relation in omega. So what this simply does is we take the relation omega, the order relation omega, and we take out all the elements on the diagonal. So n less or equal to n, 9 less or equal to 9, as we had in the example before. And this basically turns it from a reflexive relation to an irreflexive one. Now I will prove that this is a strict order, even though it's probably quite obvious. So by construction, omega and the diagonal relation have empty intersection because we just define omega hat by taking out the diagonal. So there is no element x such that x omega hat x is true. And that means omega hat is irreflexive. Now for the transitivity of omega hat, if we have three distinct elements, x, y, z, then it simply follows from the transitivity of the original relation omega that x omega hat y and y omega hat z imply x omega hat z. Because if they're all distinct, we could just drop the hat here and then it would be true for the original relation omega, and thus it's true for three distinct elements. Now if we have the case that either x is equal to y or y is equal to z, then either x omega hat y or y omega hat z does not hold. So in this case, there's nothing to prove for omega hat because one of these relations is not true, so we would not get the case where we have to show transitivity. And if x is equal to z, then x omega y and y omega x hold in our original order omega. And by the anti-symmetry of the original relation omega, this actually already requires x to be equal to y. And then x omega hat y does not hold because y is actually the same as x. And so this case also poses no requirement on omega hat to show anything about transitivity. So it follows that omega hat is transitive, and in addition to being irreflexive, that makes it a strict order. And again, even though this may be for beginners a bit confusing to define the strict order like this, it says nothing else but that omega hat is the order omega without saying that identical elements are ordered, are comparable to themselves. Now we'll look at a few examples to get a better understanding of order relations. An important example is the subset relation, and this actually gives us an order on the power set of a set. So X is a set, Px in our usual notation is its power set, and then the subset relation defines a partial order on the power set of X. We will check this. It is anti-symmetric because if A, B are subsets of X and A is contained in B, but also B is contained in A, so A subset of B and B subset of A, then we know this means the sets A and B are identical. Because it just says that every element of A is contained in B and also every element of B is contained in A. So they must be the same set. And yeah, this means the relation is anti-symmetric. It is reflexive because every subset A of X is a subset of itself. A subset A, so it's reflexive. It's transitive because if we have three subsets A, B, C of X, and if A is contained in B and B is contained in C, then A must also be a subset of C. Okay, because every element of A is contained in B and every element of B is contained in C, so that means every element of A is contained in C. Now, a difference to the order of the natural numbers is now that this is not a total order. So there can be subsets A, B and X that are not comparable, so that neither A subset B nor B subset A holds. And as an example, take this. X is a set containing the numbers 1 and 2. And if A contains 1 and B contains 2, then these two subsets are not comparable. Neither one is a subset of the other. And the associated strict order, subset equal with a hat, is the proper subset relation, which we denoted by this symbol here. The next example are divisors. So we look at the divisibility relation on the natural numbers. So if we have two numbers A and B, then we use this notation here, A bar B, or we read it as A divides B, which is defined by A being a divisor of B. So there exists some natural number n such that A times n equals B. And this is a partial order on n. It's clearly reflexive because A divides itself, because we can just multiply it with 1 to get A again. It's anti-symmetric because if A divides B and B divides A, then there exist m and n in the natural numbers such that A times n equals B, but also B times n equals A. So if we plug this expression here into the second one, then we get A times n equals A. What does this mean? Well, if A is equal to 0, then clearly B must be equal to 0. And we're done. And similarly, if B is equal to 0. So we assume that both of them are non-zero. Then this last one here, A times n times m equals A, implies that m times n is equal to 1, because we can just cancel the A on both sides. And m and n are natural numbers, so the product of two natural numbers is 1 precisely if both of them are 1 already. So we get m equal n equal 1. But if we plug this back in here, this means nothing else but A being equal to B. Which proved the antisymmetry. If we have those, then A equal B should follow. Now, transitivity. Suppose that A divides B and B divides C. This means, by definition, that there are some elements mn in the natural numbers such that A times n equals B and B times m equals C. Okay, now we can plug this expression for B into the second equation and we get A times m times n is equal to C. But yeah, this means nothing else but that A divides C, because we have some number here that if we multiply it by A, then we get C. So this proves the transitivity of the division relation. And this is also not a total order. For example, neither the number 2 divides 3 or the number 3 divides 2. So not every pair of elements is comparable by the divisibility order. Now, if b is not 0, then a dividing b implies that a is less or equal to b. So if we restrict the divisibility relation to the positive natural numbers, then it is actually a subrelation of the less or equal relation, of the subrelation of the natural order of the natural numbers, of the positive natural numbers. Now we get a bit of an unusual example, which, well, actually is not so unusual, but it's a bit tricky to define properly. So the lexicographic order is the order in which we would look up entries in a dictionary. And to make it simple, I use a particular example here for an alphabet. So if we're given an alphabet of symbols, let's just say A, B, C, D, E, F, G, and so on, so the usual alphabet, then there is an order on this set A, on the alphabet, given by the usual ordering of letters in the alphabet. And now let A star denote the set of all words formed by one or more symbols from this alphabet A. So, more precisely, A star is the set of words W, which are composed of letters L1 to LK. So here the dots, writing these letters next to each other with the dots doesn't mean I multiply anything, it just means that I write one letter next to another. So this is to be read as a string of symbols. So this word, A star, contains these words, which are made up of letters L1 to LK for some number K that's positive. So they have at least one letter, and each letter is taken from our original alphabet A. And then we define a relation, which I use this symbol to denote, and I also read it as less or equal. So we define this relation less or equal on the set A star, so on the set of words formed by letters from the alphabet A, as follows. Word W is less or equal word V if W is a prefix of V. And what this means is that if L1, LK are the letters that make up W, then V begins also with the same letters, L1, LK, but possibly has some more letters following them. Okay, so then we say W is a prefix of V, and in this case we say W is less or equal to V. Now, if W is not a prefix of V, then we have the next two cases. We also say W is less or equal to V if, again, L1 to LK are the letters making up W, and L1 prime to Ln prime are the letters making up V. And if the letter L1, so the first letter in W, is less or equal than the first letter in V, measured by the original order in the alphabet A. Okay, so we compare the first letter. If W is not a prefix of V, then we compare the first letter, and if the first letter of W comes before the first letter of V, then we say W is less or equal V. Now it could be that even though W is not a prefix of V, they share some common letters in the beginning of the word. So in that case, we just go to the first letter, let's say LK plus 1, that is not identical in W and V. And then we say W is less or equal V if the first distinct letter in W is less or equal the corresponding letter in V. So this is a bit complicated to write down, but it's actually exactly what you do when looking up words in a dictionary. And this is an order on the set A star of words formed from letters in A, and it's called the lexicographic order. And I'm not going to torture you with explicitly checking all the order properties here. If you feel like it, you can do this as an exercise. but I think it's easy enough to believe that we inherit most of these properties from the original order on A. And of course we can play this game with any alphabet on which we define an order on the letters in this alphabet, so it doesn't have to be the usual A, B, C, D, and so on. Our next example, levels in trees. So recall we just learned about trees in the section on graphs. So let T be a tree with vertices V and edges E. And by the level of a vertex V, we mean the number of edges in the unique path connecting V to some distinguished vertex, which we call the root of the tree. So very often when you graphically depict trees, you have some vertex at the top, which is the root, even though there's no unique way of picking the root. It usually has to depend on the context, what makes sense to choose the root. Here in this picture, the highest vertex would be the one I choose as the root. And we can then define a strict partial order on the vertices of T by saying vertex 1 is less than vertex 2 if the level of V1 is less than the level of V2. Okay, so here we see it. We see the levels. These two just have one edge between them and the root. These 5 vertices each have 2 edges between them and the root, and this one on level 3 has 3 edges between it and the vertex, the root vertex. Now we can say this one is larger than this one, or the other way around, this one is less than this one because it has a shorter distance to the root. But among these 5 vertices we cannot compare them. So we couldn't say this one is less than this one or the other way around, because they're on the same level already, and our relation does not say anything about vertices on the same level. And the irreflexivity and transitivity of this strict partial order here follow directly from those corresponding properties of the usual order of numbers if we apply them to the levels, because the levels are just natural numbers that are ordered by the natural order. And as I noted before, vertices on the same level cannot be compared with each other. Well, recall that I said graphs are a great way to visualize relations, but for order relations, these graphs can become very messy, and you see this in this simple example here. This is the graph for the divisibility relation, which we just had in one of the previous examples. And I just restricted to the finite set of the numbers 1 to 15. And it already looks like this. So, for example, you see that 4 divides 8, 2 divides 4, but 2 also divides 8. And of course 1 divides 8 and 1 also divides every other element in this graph. And here I already left out the loops because every element divides itself. So in principle, each vertex here would, in addition, have a loop connecting it to itself, but that would just look too horrible and you wouldn't see anything anymore. But yeah, if you follow the arrows in this graph, then you will actually see that it is the graph for the divisibility relation. For example, 5 divides 10, 5 divides 15, and so on. Now, obviously, a lot of the edges seem redundant here because they don't add information to the graph. And removing all of the highlighted edges here would not reduce the information in the graph due to the transitivity of the order. So, for example, this edge here from 2 to 8 could be recovered by simply taking these 2 edges here. That's the transitivity. If we know 2 is related to 4 and 4 is related to 8, then we know by transitivity that 2 must be related to 8. So it would be unnecessary to include this edge in the graph because in principle it can be recovered from just having these two edges. And removing all these edges that go over more than one level in this graph would actually greatly enhance the clarity. So how can we do such a thing systematically to remove redundant edges in the graph of an order relation? And what does redundant here even mean? So by redundant edges in an arbitrary order relation omega, I mean those edges that are required by transitivity, so that have to be included in the relation because transitivity demands it. And these are precisely those edges, v1, v3, such that there exists some vertex v2 with v1 omega v2 and v2 omega v3, and v2 not being identical to one of v1 or v3. So then this edge would just be precisely an edge that is required by transitivity to exist in the relation. Now if we assume for a moment that the order omega is a strict order, then we could ignore this constraint here. Then such edges here correspond precisely to the elements in the relation omega squared, which, as we recall, is just omega composed with itself, which by definition is the set of those pairs v1, v3, such that there exists v2 with v1 omega v2 and v2 omega v3. So precisely this. Now if the order is not strict, then if it's not a strict order, then it has to be reflective. And this means v omega v would be true for all vertices v. And in the graph, this would give rise to a loop at every vertex, and these are also redundant. They don't contain any real information about the order, so we also wish to remove them. So in order to obtain a simplified graph that contains all the relevant information about the order omega, we do the following. First, we replace omega by its associated strict order omega hat by taking omega without the diagonal relation. And that takes care of the loops, so this removes the loops we would have at every vertex for a non-strict order. Now, next we remove the redundant edges. So we remove this set here because we just identified this set omega square as the set of redundant edges. And that means we replace omega hat by omega hat without omega hat square. And the resulting graph for this new relation omega hat without omega hat squared is called the Hasse diagram for the original order omega. I will illustrate this in an example. So this is the Hasse diagram for the divisibility relation on the set x from 1 to 15. So you see this is a much clearer graph, so it's very easy to infer the relations from this one. It has much fewer edges, especially those pesky edges going out from the vertex 1 to every other vertex. And this is a much nicer way of visualizing orders, and especially if you somehow process them computationally. The Hasse diagram contains all the information you need for your order relation, but with much fewer data. Now, as a little exercise for you, pause the video for a few minutes and draw the Hasse diagram for the subset order on the power set of the set X containing the elements 1, 2, and 3. And here's the solution. We have this graph here is the Hasse diagram, where the empty set points to the sets with one element each. These point to the subsets with two elements each, and they in turn point to the full set X, which contains 1, 2, and 3. And remember, if this was not the Hasse diagram, but the full graph for the subset relation, then, for example, the empty set would have an arrow to each other set in this graph, because the empty set is a subset of any set. And these three sets here also would point all to the full set down here. So we would have a lot more edges that would make the graph messy. And next, and the final topic in this lecture, are upper and lower bounds in ordered set. So we assume we have a partially ordered set X with this partial order, and we let this denote the associated strict partial order. And I will just use the words less or equal and less again for these orders. An element X in our set big X is called minimal if there's no element Y such that Y is strictly less than X. The element X is called maximal if there's no Y, no other element Y such that X is less than Y. X is called a least element if X is less or equal to Y for all elements Y in our set big X. And X is called the greatest element if Y is less or equal to X for all elements Y in our set big X. So these definitions are rather straightforward, but it's important to note that minimal or maximal elements do not have to be comparable to every other element. So if we have a minimal or maximal element, then it could be, for example, that X is minimal. So there's no Y that's less than X, but it could be that there are elements Y that are neither less or more than X. So they cannot be compared to X. And also, least and greatest elements do not have to exist in a set, but if they exist, they are unique by the reflexivity of the less or equal relation. Now, if we have a partially ordered set, X with the order less or equal, and we have a subset Y of the set X, then an element U in the full set X is called an upper bound of the subset Y, upper bound in X to be precise, if for all elements in the subset Y we have that Y is less or equal to U. Okay, so note that U itself does not have to be contained in the set Y, but all elements in the set Y, in the subset Y of X, have to be less or equal to U. And now among all the upper bound, a least upper bound, or also called a supremum, written sub Y, of the subset Y in X is a least element among all the upper bounds of the subset Y. So among all the elements that satisfy this, if there's a least element in this sense here, then we call this the least upper bound or supremum of the set Y. And analogously, we have the following definition of a lower bound. So an element L in X is called the lower bound of the subset Y in X if L is less or equal to all elements in the subset Y. And again, it's not required that L itself is contained in Y, just has to be less or equal to all the elements in Y, but could be an element of X that's not in Y in principle. And now a greatest lower bound or infimum of the set Y in X is the greatest element among all of these lower bounds of the subset Y. and we finish by looking at some examples. So consider the natural numbers with the usual order again. Then 0 is the least element of the natural numbers, but there's no greatest element, because for any element n in the natural numbers you have always n plus 1, n plus 2 and so on, so you cannot find the greatest element. Now every finite subset y of the natural numbers has both an infimum and a supremum, simply taking the largest and smallest element of that set itself. And so in this case, infimum and supremum are both contained in the set y. And if this is not clear to you, you can prove it by induction on the cardinality of the finite subset y. In the integers, there are infinite subsets without lower and upper bounds, such as the integers themselves, or any integer multiples of some natural number. So the even numbers, or the multiples of 3, or the multiples of 4, or something like that. And you can think of many other examples of sets that have no upper or lower bound. Now in the rational numbers, we have some more interesting sets. So for example, look at this set y, which contains all the fractions 1 over n, where n is a positive natural number. Then as n grows larger, so as n tends to infinity, as they say in analysis, the fractions 1 over n get arbitrarily close to 0. So this means the infimum of y is 0, but the number 0 itself is not contained in y. So here we have an example where the infimum of a set exists, but it's not a part of the set itself. And yeah, to prove this, you would have to use some of the techniques you learn in analysis. But it's easy to believe, so we just accept it here. And as for the supremum of y, we have the element 1, which equals 1 over 1, so it's clearly an element of the set y if we plug in the number 1 for n. So this is the greatest element of y, and hence also the supremum of y. And in the real numbers with the usual order, we have the open intervals. So these are the sets, or the open interval from AB is the set of all real numbers that are strictly larger than A, but strictly smaller than B. So this set has the infimum A and the supremum B. But neither the infimum nor the supremum is actually contained in the interval. On the other hand, we have the closed intervals, written like this, with brackets, AB, which consists of all the real numbers that are greater or equal to A and less or equal to B. And here again, A is the infimum and B the supremum, but in this case, infimum and supremum are both contained in the set. And another example, the subset order on the power set of X for an arbitrary set X. If we have two subsets AB of X, then they have a supremum, or more precisely, the set containing these two subsets A and B has a supremum, which is the union of the two sets. Now, to see this, note that clearly A union B is an upper bound for both the set A, or the set containing A, and the set containing the set B. Well, because A is contained in A union B and B is contained in A union B. And if there was a smaller upper bound, let's call it S, with respect to the subset order, then we would have the following: AB subset equal to S, which would be a proper subset of A union B. But if this was the case, then there must be at least one element of A or B which is not contained in S, because this is just the set containing all the elements which are either in A or in B. So one of the elements of A or B would not have to be contained in S, but that would contradict one of these two. So either it would contradict A subset S, or it would contradict B subset S. And that means there can be no lesser upper bound. And this means A union B is the least upper bound of the set containing the subsets A and B. And in a similar way, you can convince yourself that the infimum of the set containing A and B is the intersection of the subsets A and B. And yeah, so this is a rather interesting application of the concepts supremum and infimum. And with that example, I'm at the end of this lecture on relations. And there will be another lecture coming up on equivalence relations, which is probably the most important class of relations, and they well deserve having a lecture dedicated fully to them.